Saxon Algebra 2, Lesson 51. This is a red letter day in your mathematical life because we are going to talk about imaginary numbers. They are fascinating little creatures, and you may have heard me hint about it recently, but for the most part, you probably had no idea that these things existed. They've been lurking in the shadows of your life all this time, and today they're boldly stepping out, and you are going to learn all about them. All right, before we talk too much about what they are, let me show you how they arise. And example 51.1 gives us some great little examples that will help us see how they come about. So let's take a look at a scenario like this. We're multiplying the square root of 3 times the square root of 2. We can simplify that. I'm doing this the long way just so you can see. We can put these two guys together into a pig house, right? Two pigs in separate houses can move in together, and then that would simplify to the square root of 6. That is a perfectly fine number. Let's look at another one. This time we have a minus sign on each of them. Now, what we can do is think of this as we're going to put them together in the same house, but what we can do is we can break each of these into minus 1 times 3, minus 1 times 2. You see how I'm taking the minus sign and kind of separating that, keeping the number itself and then putting the minus sign in front of a 1 to sort of package it separately? Now we can say that these two minus 1s are two pigs in the house. We'll bring them out as a single pig out of the house, so that will be a minus, and then we'll have the 3 and the 2 left inside. That gives us a 6, all right? So by separating these numbers to keep their minuses separate from them, this becomes a perfectly fine, lovely number. And so what we can say right here is that examples of multiplication with radicals, like A and B, they are, I'd go so far as to say they're A-OK, which is to say they are real numbers. All right, that's perfectly fine. This next problem is we're going to see where the problems kick in. Let's say that we're multiplying 1 positive root times 1 negative root. Okay? We can squish them all together like we did last time. We can separate the ones, the minuses from the numbers, right? This one would be 3. This one would be times, this is times, minus 1 times 2, right? We're separating the sign from the number just like we did last time. But now it's left inside of pig house. We can't take that minus out. So what we're left with, and I'm going down another line, is the square root of minus 6 with, this is the alarming part, there's a minus sign inside the pig house. That is real trouble. Now, if this were a cube, or in any odd numbered root, that would be okay. But when we had even numbered roots, especially the invisible 2, right? We haven't been writing the 2, but we know it's a square root. Even numbered roots cannot have minuses on the inside. There's no way to find that number on the number line. It doesn't exist. So when we have a minus inside of an even numbered root, that's how we get an imaginary number. And again, what that means is that it is not located on the number line. You can't graph it, right? On just a basic little number line, it doesn't show up anywhere. It's not a real number. It is an imaginary number, okay? So this is our first example of looking eyeball to eyeball with an imaginary number. Now, I want to tell you about a man named Euler who spells his name in a quite remarkable way. It's spelled like that, but it's spoken like this, like Euler, right? He was a Swiss gent from Switzerland, and he lived in the 1700s. Now, he was cool because he came up with new symbols, and I love that. I love the person who thinks of easy ways to write things. So he was really big on coming up with notation for ideas in math that needed to be expressed in a written form, and coming up with a neat little code for doing that. He came up with this idea of using the sigma letter for summation. I don't think we've done this yet, but we will soon. I think it's in advanced mathematics. This is a special symbol that means summation. It's really fun and easy to use. He also came up with what we call functional notation. Function notation, right? He's the one we have to blame for driving us crazy with this stuff. He also came up with something that we'll learn later at the end of this year. Logarithms based on e, which is a number approximately equal to 2.71. It behaves kind of like pi in that it's a constant that has a lot of decimal places, and we just use a letter instead of writing that number all the time. We'll talk about this later also. And then the fourth thing that he is famous for coming up with is using the letter I for imaginary numbers. And that's what we're going to talk about next, is how do you identify and write a number differently when it is an imaginary number. And we have Mr. Euler to thank for that, our lovely Swiss gent. Okay, turning the page. Oh, look, we're almost to the back of the book. So let's take our imaginary number that we just created. It was the square root of -6, all right? So again, minus sign in an even-numbered pig house is the problem. So what we do is, once again, we split the -1 separate from the number itself, and then we recognize that thanks to Mr. Euler, the square root of -1 is called I. Okay? So what we do is we take this, and we can, just to show you the longest, slowest way of thinking about this, we can now put these back into separate pig houses. This, according to Euler's rule, this we're going to rewrite as I. So this will be equal to square root of 6I. That is the way we write an imaginary number. Notice that the I is outside of the pig house. It's not inside. You don't have to take the root of it. It is outside, and what it signifies is that this is an imaginary number. It's not a real number. It represents this minus sign, but it's not there anymore. So a couple simple examples to just help illustrate this. Square root of -13. We see the minus sign. We recognize that we could split it apart. I'll just write it apart so you can get the idea of it. It would be -1 times 13. This turns into an I, so it becomes square root of 13I. Okay, how about this? Square root of -4. Okay, mentally, this is what we're doing. You won't have to write this out in such detail once we get into it, but I just want to make sure you see how the pieces are flying around. This one, we can do the minus sign separately, and then we know that 4 can be broken down into 2 times 2. In this case, this is going to come out as an I, and 2 pigs in the house will come out as a single one out of the house. So look, sometimes we can have imaginary numbers that are integers, so to speak. They're not really integers because they're imaginary, but they don't have to always live in a pig house, right? We can have them like this as well. All right, and then calculations. This is like the one we already did. Square root of 3 times the square root of -2. What would we do? We change this, as soon as we see a negative sign inside of a square root and we recognize it as an imaginary number, we change it immediately. So we would change this to square root of 2i, right? We mentally separate that into a -1 and a 2. The -1 root changes to the I, the square root of 2 stays the same. Now we multiply the rest of it, and we would get square root of 6i. Okay? So this is example, I didn't write this down. This is example 51. Oh, this is 51.1. Look, I've been doing these examples and not even telling you they were examples. So this is number 2. Oh yeah, I did. 51.1 back there. All right. So we're learning just enough to be dangerous with these imaginary numbers. Let's keep going. I have a little bit more to explain, but we're getting there. Now, that's what an imaginary number does. But sometimes we combine imaginary numbers with real numbers. And what we call that special concoction is a complex number. They always take a very specific form that looks easy and painless, right? A plus bi is the form of a complex number. And it has a very simple structure. The part in the front, the A, that is the real number. And then this, you probably recognize, this would be the imaginary number. We always put the real number first and then have the imaginary number separate. If these were over a fraction, we would separate them into 2 separate pieces. Okay? That's very important. The other thing I want to tell you, and I'm going to write it up here by this, is that if you have 2 i's, I squared, that equals -1. I'm not going to burden you with the theory of it, but basically, if this is equal to I, then that is equal to I squared. These 2 rules, I want you to accept. I want you to write them down. I want you to carve them into your brain. I want you to carve this into your brain. That is an ugly expression. I want you to memorize it. Don't carve it into your brain. That sounds like cutting in an extreme form. And you know what? I don't want you to do that either. P.S. I just want to take a side note and say, COVID sucks for everyone, but man, it is really hard on teenagers, isn't it? It's really, really hard. It's got to be. I mean, I'm not a teenager. I don't know. But it's got to be really hard to keep pushing and think about building up your life in a world as crazy as this COVID world has been. So I just want you to know I recognize that, and I appreciate that you're chugging along with me and doing your math and trying hard to make life seem normal. And I don't often acknowledge that. But I want you to know that I get that this is especially hard on teenagers, this whole crazy thing that our world's been going through. It's hard on everyone, but the more settled a person's life is, the easier it is to kind of roll with the waves of COVID, right? My life is pretty settled. And so it's not as crazy for me. You guys are teenagers, your lives are changing. That's so much more unsettled. Anyway, it makes me sad. So I'm sorry for what you're going through, and I appreciate how hard you're working to keep this going, this crazy math business. Right on top of everything else, the world's imploding. We don't know if we're going to survive. Is the vaccine going to help us or hurt us? And you're like talking about complex numbers and some dude from the 1700s named Euler. I mean, it's hard to have priorities like that, and I appreciate that you do. Okay, 51.3. What we're going to practice doing now is working with some complex numbers, creating, combining. It's pretty straightforward. John tells us to add these numbers. Okay, so there's a string of numbers. Some have i's, some don't. We treat them just as if the I was any other variable, right? And we just look for like terms. Here are our two real number pieces. 4 minus 2 is 2. And then here are our two imaginary pieces. And they add up to 9. So our final answer here is 2 plus 9i. That's pretty straightforward, right? Okay, notice how we've kept our format clean and pure. Okay, let's make it a little tougher than that, because that was pretty easy. We have a total of 1, 2, 3, 4, 5, 6 examples, and we're on number 4 right now. 51.4. Okay, now this one looks a little more confusing, but don't worry, it's not too hard. What the heck? I've got multiple i's stacked up on the outside of these numbers. I know that they're imaginary numbers, but they look weird because we've never seen multiple i's before, which also sounds weird. And what's all this? That looks confusing, doesn't it? All right, we'll break it down according. First, let's remember our rules. I equals the square root of minus 1. You can write this in either order. It doesn't really matter, whatever appeals to your brain. I squared equals minus 1. Okay? Now we can use this one in particular to help us with these multiple i's. For every pair of i's that I have, that's an I squared, and that's equal to a minus 1. So that means this simplifies to minus 2. There's no radical sign, so that's perfectly fine. This is a real number. Here we have 3 i's, so I circled 2 of them, and I put a minus 1 above. That tells me that these two simplify to minus 1. That's going to change this to a positive, isn't it? I circle it to show that I changed it. And then we'll have 1 I remaining. So this will be plus 3i. Okay. Now we have another 2i. Yeah, I copied the wrong problem. This is actually 51.5, but that's okay. We'll figure it out. Minus 4 is good. This changes. Right? This we know, okay, the 4, square root of 4 changes to just a 2. And the square root of minus 1 changes to an I. So this is going to become a minus, that stays the same, 2i. See how I took care of each part separately? The square root of 4 is the 2. The negative 1 becomes the I. Excuse me. All right, now we have cleaned all of this up, and now we're ready to go through and just look for real numbers and imaginary numbers. Let's start with the reals. Remember, we want this format for our answer, the proper form of a complex number. We want the real pieces first. So that's minus 6, and then we'll take the imaginaries as a clump. That's plus 2 and minus 2. I can see those cancel each other, so it will just be plus 3i. Okay, that's the right answer. I took this out of order. This is actually 51.5. So let's go back and do 51.4. And that looks like this. It says add. And what John has done in creating this problem is he has taken 3 complex numbers and he's written them in parentheses. Right? Complex number, complex number, complex number. See how they each have the a plus bi? It's okay if it has minus signs. That doesn't change it. But he's given us 3 complex numbers written in clumps. And what we want to do is get rid of those parentheses and be able to combine the matching numbers. So this one does not have a minus sign or anything in front of it, so we can just take that off. 4 minus 3i. This one has a plus sign in front of it, so we can just take this off. This is the tricky one. We have to essentially distribute the minus sign. So this becomes minus 2 plus 5i. All right, so old rules apply. Even though we've got imaginary numbers thrown in here, we manage them following the same set of rules. Thank goodness. Can you imagine if it was like a whole different world of math and we had to switch gears? Oh, that would be weird. That would be trippy. But this is kind of more like the upside down in Stranger Things, where we're upside down, but everything is still following the same sense of order. Okay, now we're ready to combine. Let's do real numbers. I'll circle real numbers. There's 2 little kids that live across the street from me, and they have trouble saying their owls. And so sometimes in our family, not in a mean way because we adore them, but we will say things without our owls. And one time the little boy, who's like 7 or 8 by now, he said, "I can't say my owls." So that's a famous quote. And their dad's name is Rick. And the kids refer to their dad. They call him Dad, but sometimes talking to us, they'll say Wick. "Hey, Wick." We talk to our dad. His name is Wick. And so that's always fun too. So when we're talking about the dad in our family, we'll always say, "Oh, Wick was out doing his lawn the other day." And maybe I'll say it to him someday. I don't know. Okay, 4 plus 6 minus 2. That's 10. Minus 2 is 8. Minus 3 minus 4. That gives me minus 7. Plus 5 is minus 2. Okay, so those rules are very simple for combining them. Here we had to be careful with the parentheses. Here, as you can see, this one was a little easier than this one. Here we got into the situation where we have multiple i's and we have to use this rule to simplify. And we have one more. $51.6. All right, simplify. Now look at how this problem is written. This is a little bit of a head game. Okay, so last time John wrote out the I 3 times. This time he's using exponents. This is the rule we're going to need to do this kind of problem. What we know is that for every 2 i's, we can switch the sign in front, all right? Now, if you like, some students find it more helpful, especially in the beginning, to write out the individual i's so that they can circle and kind of work out the problem a little bit more carefully. Some students have no problem visualizing this and just leaving it in exponential form. If you're at all confused by this, I recommend that you do it this way in the beginning. You'll pick up speed and get better as you go, get faster as you go. I'm gonna do it this way, and if you wanna go faster, that's cool. All right, so here's 3 i's. 2 of them turn this to a minus sign, and so this becomes minus 3i. That's the one left over. These 2 completely wipe out the i's, change this into a minus sign, so it's just minus 2. This we can't do anything with. This we don't do anything with. Here, oh, look what happens. This is a minus 1, but this is also a minus 1. So the 2 minus 1s go together to equal a positive 1. That means this sign doesn't change. The 4 of them knocked each other out. We still have 1 left over, so this stays positive 2i. That's kind of tricky when you get the 2 negatives turning each other into a positive. All right, and so our final step on this one is just to combine these again. I'll circle the reals. That is positive 2, and then all of these guys. Remember, it's just like any other variables. We can ignore the letter and just follow what the coefficients are doing. This is 9. This is a -3. That would be a +6. Is that the right answer? Yay! Okay, so once again, I want you to make sure, here's a good place where they're all written down. Make sure you understand these rules and you know the proper form for complex number. Get these written down in your notes and remember them fondly from this day forward. You now understand that there is a world in which imaginary numbers roam free, and it is our world. And now you know about my friend Euler. What's his first name? You don't care, but I do. You might care. Oh, it just says Euler. It doesn't have his first name. Dang. He was a very fancy mathematician. He was a cool guy. And I love him. And I love the things that he invented to make writing about math easier. Okay, that's all. Lesson 51 is done. Yay, bye.